Oopsie, that's a G. They gave the distance in millimeters. How do we convert from millimeters to meters? Times by 1,000?
Isn't it the same thing?
Divide by 1,000.
Oh, divide.
Okay. And you get an answer, Nimukatsu, of what? -8 newtons. Good. Okay. Now the side B, if the masses move so that their distance is now a meter from one another, what will happen to the force? Okay. Just wait. Okay, so you can now do it in one of two ways. Okay, question B. You can either redo this whole thing, 6.67 times 10 to the negative 11 times 10 times 25, thank you, times 1 squared, okay? Or you could have said, all right, what happened with my distance? It was 0.5 meters, now it became 1 meter, right? So what happened? It doubled. Okay, so we can say F2 now has G M1, M2 over 2R, and the whole thing must be squared. So we now have a quarter GM1, M2 over R squared, or a quarter F. Sharp? I'll show that in the notes on that other page. Okay, so this is the quarter of F. F was that value there. So we can put that in there. Sorry. 6 points. And you get the answer to be what?
1.67.
Negative?
8. And newtons.
Okay. Why am I showing you the second option? Because this is normally how they ask in a multiple choice question. So I want to practice that multiple choice concept. Okay? But if you did it like this, it's fine. Where did I get the 2 from? The distance was 0.5 meters.
Okay.
And now it's 1 meter. So how do you go from 0.5 to 1? Where's your glasses? Yeah. This whole day, you haven't worn your glasses once.
Let me wait then because I'm in your class. I'm very special.
I'm going to call your parents and tell them you're wasting their money. That's true. Okay. Now the side question C. If the size of the masses and the distance is doubled from A. So the masses are doubled and the distance, how will the force change? So now we have G 2m2 over 2r squared. Okay, so that is 2 times 2 gives you?
4.
2 squared is? 4. So it is exactly the same as F, which is 6.67 times 10 to the power negative 8. It stays exactly the same. Now, if you multiply both masses with 2 and the distance by 2, you should get the same answer. Perfect, fine. What's wrong? What's wrong, Butamilu?
Yeah. I didn't think about it. I think it was also, I didn't know.
Oh.
There are 2 decimal places.
But if you don't round off, it's also fine. But if you round off incorrectly, it's wrong. So rather don't round off. Yeah. Go for it. For writing the whole thing. Are you done? Sharp. Okay, then question 9. Okay, it says there you have two masses and they're 2 millimeters apart. So the first mass they give us is 2 times 10 to the power negative 4. The second mass is 5 times 10 to the power negative 5. And they say the distance is 2 millimeters. Okay, the masses already give us in kilograms, but the distance is in millimeters. Fatima, millimeters? Wait. Alright, now they ask, what is the gravitational attraction force between the two masses? So again, we're going to go to Newton's gravitational law. What if you win? Did you see I added you to the group for your brother? Because he doesn't have a cell phone. He told me he doesn't have one. So I said, then I'm going to add you. And he said it's fine. But you can send me his number. Newton's, no, wait. Moses is going to do the calculation. From you, I want to know Newton's gravitational law in words. I'll do the first part. Any two objects in the universe will attract each other with a force that is.
What is that wave?
With a force
With the force
that is.
equals to the mass.
Nee.
Inversely
Out of the way. Nee, bo die lyn. Is nie inversely nie. Directly proportional to the what of the masses?
One of the masses.
Product
Bodies.
of their masses and inversely proportional to the radius between their centers squared. What if I'm going to ask you again? Okay, Moses, are you on it? Is someone checking Moses?
Moses is in his own world.
I'm busy here.
Yes, Moses. Say again? And don't delete. I want to see what you type.
Isn't it the same as the other answer?
So this whole thing you type in next to it. Yeah, you do use that button.
18.
One 1.67.
Times 10.
Okay. Now they ask if the distance is changed to 10 millimeters. Okay. Wait. Say again. Okay, yeah, just give me a moment to finish my sentence. The distance was 2 millimeters. Now the distance is changed to 10 millimeters. So the difference is 5. So when we go to our formula, it's G m1 m2 over 5r squared. Right? So that is a 25th of the original f.
No, please don't do it that way.
I need to practice it in that way because they ask a lot of these questions.
This one is really confusing.
Gives you 6.67. As you write down, make sure you understand what you're writing down. If you don't understand, please ask.
Then that top part is one, like GM1,
No, it's not one. That top part with r squared, okay, is the same as this, which was equal to that. Remember we did it
I can see
Monday.
5 squares, 25. And look out.
Any other questions? Yes.
The thing is 13 or 15? The 12 is 15.
13, 15.
Yes, because you... Oh, I didn't get to round it off. Okay, so she's saying, ma'am, I got 6.68. How did you get 6.67? Because I kept this long answer in my calculator here. Okay, so if you have 6.68, it's fine. Yes.
How do we get A by C? The previous question, HC. How do you know whether it should be G, 2M1, and 2M?
Because they say the masses were doubled. Both masses were doubled. All right. Then I want to go back to your notes. Notes. Okay. Right. Now we're going to go to gravitational acceleration. Gravitational acceleration. Okay, I'm going to read and then I'm going to explain. It says there, free fall, so the concept free fall, occurs when an object falls under the influence of gravitational force only. So free fall is when an object doesn't have mass, not a mass, there's no air resistance and it falls and it's just gravity pulling it down. There's nothing else. No one is pushing it, pulling it, nothing like that. It's just gravity pulling it down. That is called free fall. Due to the gravitational force of attraction between two objects, these objects' acceleration is called gravitational acceleration in meters per second squared. So due to gravitational force, the acceleration is gravitational acceleration. Say again?
What's the first way we can say that?
Why?
What's the first, like, you see the second law, remember what you did for the second law?
What?
Like if need
F net, M, we
Yeah.
don't know F net, whatever. This one is a lot, how can you just like,
No, this is not a law.
a lot?
Yeah, but this is not a law. You don't have to know all of this off by heart. If something is in a block, it's a definition, it's a law. I'm just explaining something now. Alright. Okay. Gravitational acceleration, and that's always directed towards the center of the earth. So if something falls, why does it fall? Due to gravity. How fast does it fall? Gravitational acceleration, 9.8. Now, if air resistance is ignored, then G is the same for all falling objects. Okay, so that is what we are going to do here, is we are going to prove that it doesn't matter if you take a rock or a feather or a human or a tree or a whatever. That 9.8 that we calculate, that we use the whole time, that is the same for all objects. That's what we are going to prove here. Okay, so when we calculated Fg, how did we do that again? We said m times 9.8, which is g. Okay? Alright. So what is that actually? That is the force with which the earth pulls you down. So that is the attraction force between you and the earth. So that's the same as F is GMM over R squared. Just look at the M's that I use. I'm going to explain it now. So this Fg is the force with which the earth pulls you down. So it's the attraction force between you and the earth. It's the same thing that we just did. Okay? Now you can see I changed the formula here a bit. What did I do here? Small m refers to you as a person or object. Big M always refers to the mass of the planet or the moon or the sun or the whatever you're standing on. Okay, so you're allowed to do this. Small m refers to the mass of the object. Big M refers to the mass of the planet or whatever moon. Okay. So, since these two mean the same thing, what's going on? What's wrong? Well, okay. Well. Alright, since both of them calculate the same thing, we can put them equal to one another. So we have mg is equal to gmm over r squared.
What? Oh, it's times. Mg is times.
They calculate the same thing. This is the force with which the earth pulls you down, and this is the force between you and the earth.
So mg, what is mg?
M times g, m times 9.8. G is the gravitational acceleration, 9.8. Alright, now this is the mass of you, the object. This is the mass of you, the object. So I can cancel them out. So G, lowercase g, 9.8 is equal to gm over r squared. So that 9.8, the gravitational acceleration, is only dependent on the mass of the earth and the radius of the earth, the size of the earth. That's why when you go to the moon, your g is different. Why? Because the mass of the moon and the radius of the moon is different. Okay, so that 9.8 does not depend on your mass. Okay, now I want to show you something here. Yes. Click here to subscribe to my YouTube channel. I don't even know how to see if someone subscribed to my channel. Wait.
Go to your settings then. Yes, go to
Your
that
channel.
Your channel. When you see this, how many subscribers?
61 subscribers, people.
When you see the other videos you're sending to us, man. Look, man. You must get paid with that. Now let's see your views. Go to the bottom one and just see the views. Just swipe.
Where?
Swipe. She has like 61.
That's more than some of you.
No, that's
Man, tell them to report your videos and dislike them.
Who? Who does that?
Let me see what the analytics are. Just swipe like this.
I can't.
Why not?
I don't know. Okay, it doesn't matter. I really don't care actually.
You must get paid.
I must get paid.
200 per view.
I will in a moment. Okay. So what? Thank you. So what's happening here? Or what this guy is?
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left.
A metal ball, very heavy.
And it's got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete
with
skin,
air
which is
resistance,
part
and then they're going to pump
radiation
out all of the
and
air.
parts and
Okay,
external
so he's just
pressure.
saying, wow,
So
look at this
thing
building,
can
oh my
take
word, beautiful,
force
beautiful.
that's present on the outside when it's
Yeah,
Galileo's
you got-
experiment was simple. He took a
They
heavy
pump it out.
object
It's like
and a light
suctions.
one
Yeah, all
and
that.
dropped them
Okay,
at
so
the
there you
same
can see
time
the ball
to see
and the
which
piece
fell
of feather.
fastest.
Piece of feather. Okay, and they're going to drop it now. And like we expect, the ball drops faster. the feather has more air resistance.
Now, in this case, the feathers fell to the
Okay.
ground at a slower
Right,
rate than the
and
bowling
he's just
ball
explaining. He says,
because
can
of
you
air
see more air resistance? Ball drops faster, blah, 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 blah. Now they go
So, in order to see,
and they pump out the air. Okay, so
it takes
obviously
3
very
hours to pump out
dramatic.
the
Look at us
800,000
closing
cubic
this whole
feet of air
thing,
from the chamber.
pumping out the air.
Dropped 2 millitorr in
Everyone
the
is
last
very
30
like
minutes.
focused.
But once it's complete, there's a near perfect vacuum inside.
What? I don't know. I can't remember. I've watched this
Station 1.
4 times a year for the
PCB
past 12 years.
30-1, pressure set point at 240 psi. PR go for drop.
Alright.
10,
And
8,
they are going to
7,
drop it now.
6,
He's looking
5,
like he's interested.
4. Cameras on. 2, 1. Release.
Okay, and they release it.
You know a movie when it's in slow mo?
If this is in slow mo. Okay. So they show you here that, can you see, it's falling at exactly the same speed because there's no air resistance. So that 9.8,
Look at that.
see, you can see there they work in NASA.
Exactly the same.
So as you can see, it falls at exactly the same speed because gravitational acceleration is the same
Exactly the
for
same.
all objects
Move
if
nothing.
there's no air resistance. Okay.
That's just brilliant.
They're like, wow, can you see? Let's show that again. Oh my goodness, again.
Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life,
People must be
the
interested.
ball and the
All right,
feathers
so-
were being accelerated towards the earth.
Okay, so that is what we showed there. That G is only dependent on the mass of the Earth, or the Moon, or the planet, or the whatever you're on, and the radius. Okay, so I just summarized it at the bottom for you. G is only determined by the mass of the Earth and the distance from the center of the Earth, so the radius. It is a vector, meaning it has magnitude, size, and direction. Then G is not a constant. Okay, but now we always use 9.8. Like, when do we use something else? We use 9.8 when we are on the surface of the Earth. When we are on the moon, or when you're up in space or whatever, then it changes. So it changes from place to place. It changes when your distance from the Earth changes. All right. Yes?
We will have to calculate the G first.
G is giving to you.
That big G. Small G.
Small G.
I might ask you to calculate it, yes? When you have the mass of the moon and the radius of the moon.
Just plug it in.
Yes. All right. So, from the equation, big G and M's are constant if we are on the Earth. Okay. But then, very important, when the radius decreases, when it becomes smaller, G increases. So they are inversely proportional to one another. Because if the radius becomes smaller, it's like you and your love interest. The closer you come together, the bigger the fire. No? All right. So, the graph that we get from there is this one. The bigger the radius, the smaller the gravitational acceleration. The smaller the radius, the bigger the gravitational acceleration. But we as scientists, we do not like a graph like this. We want a straight line graph. So if you put it on 1 over r squared, and you plot the same graph, you get it like that. It becomes a straight line graph. You need to know the shapes of these graphs for especially multiple choice type of questions. All right. So what I want you to do is, and you're going to start now because I want to check, is you are going to do questions 10, 11, 12, and 13. But 13 is actually too easy. What factors affect G on the Earth?
You just do air resistance.
No. Okay, if we're going to ignore air resistance. The mass of the earth and the radius. Okay. Okay, so you're going to do that, please. Just one more thing. Here they say a mass of 2 kilograms weighs so much on the surface of the earth. Calculate the mass of the earth. Okay. For that, you need the radius. So I want you to look on your data sheet. So quickly take